mapped with demand paging, then it talks to the operating system. And also if the address is not legal. If you've ever referenced null memory, this is involved. So that's what we're going to overload. And Intel actually creates two TLBs. First is a data TLB and instruction TLB. The instruction TLB is referenced a lot more than the data TLB, so it makes sense to optimize that a lot more. So to load instructions into the data TLB, you simply just reference memory. The move instruction on the top is how that happens. To load data into or addresses into the instruction TLB, you actually have to call into that address. So that requires backing up your memory or your next instruction with a return call, calling that, and then once you're back, restoring it. And so that'll load the address. And so once an address is moved forward here, or let's say our address is referenced, the hardware first looks to see if it's present in its cache. If it isn't, then it walks the page directory the same way the page fault handler would. If that still isn't correct, it looks, once it finds it, it says, is this page table entry valid? If not, then that's when it kicks it over to the operating system side, which is code where we can control. And then there's checks to see if it's page to disk, and are the permissions correct, and then there's errors inside of there that go there. So what we're going to actually overload is the permissions. So Saffron, there are any Firefly plans, that's where we got the name from. Saffron uses a Intel pin and hybrid page fault handler. This is inspired by the really great work of Joe Stewart, so if you're out there, thank you very much. We designed it for 32-bit Intel CPUs, and we replaced the trap handler in Windows. And we want to log memory accesses. So there's been some previous work to this. Shadow Walker by Jamie Butler and Sherry Sparks. This was used to behold my magnificence. This was used to hide memory pages inside the kernel. And this is one of the first references we found to this. PAX actually does buffer overflow protection for Linux. Ollie break on execute. This was a kernel module coupling for Ollie debug, which allowed you to tag sections of an executable and then break on that, done by Joe Stewart. And recently, Memolize by Scape. This was done for tracing memory accesses for the purposes of developing exploits. So the first one, we're not really trying to hide memory from the kernel. PAX, buffer overflow protection, we're for it, but it doesn't help us here. Ollie Bone, it still has a lot of the detection problems that Ollie debug has, so that doesn't do that. And Memolize is again, not interested in being covert. So Saffron system implementation is we first short out the interrupt descriptor table and point it at our new page fault handler and do some determination whether it's a page or a process area that we're interested in. If it's not, we hand it off to the page fault handler. And if we are interested in it, we hand it to our logging system and allow code to continue execution. And we have a process monitor that sits in RAM. And what you should take from this is that the malicious executable is we have no hooks into its memory. We're monitoring everything from the operating system. So the mechanism that we use is we overload the supervisor bit in the page fault handler. And the step is to find all the process memory that you're going to use and set the supervisor bit. And then you invalidate the TLB or flush it so that it will actually trigger an OS page fault. Once you've found all that memory, or the other way, there's a couple ways you can find the memory. You can iterate through every single address. You can iterate through all the pages, but actually what works best is reading the PE header and finding all the sections. So once a memory has trapped, we determine if we're watching that process. We don't want to hook on kernel memory or another process's memory because hilarity will ensue. Next, once we've figured out it's ours, we unset the supervisor bit, which allows us to load the memory into the TLB and allows the process to actually run it. And then we put the supervisor bit back on so we can see it again. So, modifying the unpacker that we wrote for the dynamic instrumentation version of Saffron, we watch for written pages and then executions into each of those pages. And each time we see an execution into a page, we'll mark that address as the original entry point and dump the process of that memory. And what's nice about the Intel TLB is that it actually lets you decouple those, and it sort of does a lot of the work for you. So the results from this are that reads, writes, and executes are exposed. You can see them. And program execution can be tracked and thus controlled. And each execution only shows for each page. You get the first address inside of that, but that actually turns out better. And it's extremely fast because it's running on raw hardware. So we'll go ahead and demonstrate the... So what we're going to do is take this tlock executable, show that we're run it through PID. It's actually encrypted with tlock. Tlock is actually one of the more difficult ones. And we're also going to take a UPEX encrypted version of the same executable. We're looking at the UPEX one to find the original entry point, just so we know. You don't have to know the original entry point, but it helps us here. So we run the same script that Val ran again and find that the OEP is right here. And so for this demo, we're using the same address that we know of here. Now we'll actually load the kernel module into place, which shorts out the page fault handler, sets ourselves up for logging, and those sorts of things. Now we'll invoke the user monitoring one, and we'll load up the tlock encrypted version of netbull. And this is kind of what tlock does. But you can see it finds the original entry point, and there's about 7 other addresses that are present there, and each one of them have dumps. So we'll go ahead and go look at one of the dumped files, which just deposits in the same directory. Or first we'll take a look at the tlock, the original one that's in memory, and it looks terrible. You know, we got this start address, which is pretty worthless. It doesn't let us do any sort of analysis on it. The names window, there's nothing. Basically, the executable looks like goatsy. So what we want to do is actually get to where we can unpack it. Just to look at the XREFs and that sort of thing. Start, nothing there. This is, if it was unpacked, it would be a much bigger graph. So let's actually take the file that we dumped with our Saffron kernel module. And here we can see that there's actually good information. Again, blue on that top graph represents code. So IDA's a little bit more busy, which is always a good sign. We've got functions inside of here. This is filling out. We can actually go look at those functions, and this is actual valid code. If you can read this out on the screen, it says there's a password right there. So that's a good place to start looking at. And also, the cross-references are populated too. So there's good information coming out. The flow graph of the entire executables is full.
A lot better than just start.
Yeah. We've got names. There's strings also. Interesting ones like the name of the executable and that sort of thing. So we can scroll through these. We've got registry keys. The actual name of the malware, which is probably how it got its name originally. And that's it. Okay, so the results of this is that it works. Tricks like the SEH decode problem, which tlock uses extensively to get into process memory and do the checksumming, they pretty much go away. Memory checksum, the process is able to look at it itself and look for these executions. So again, we're not looking at any of the process memory. We don't modify anything, and so things like tlock are allowed to execute. And this is pretty effective across a wide range of packers. There are some caveats, though. The system requirements for this are XP Service Pack 2. As far as I know right now, Vista isn't a real heavy target of malware, and the malware that is targeting it works on it just fine. You have to turn data execution prevention off. DEP is a method that Microsoft uses for buffer overflow tracking, and it actually plays with the page fault handler too, and it'll cause some problems. This must mean a single CPU. This is mostly because we're not supposed to be shorting out the page fault handler, and there's certain mutexes that we need access to that Microsoft doesn't want us to, because there's really no good reason for somebody to be in the page fault handler except for what we're doing. And to enable this, you have to set the one CPU flag. This is also 32-bit only. 64-bit malware is starting to pop up, but again, most of the user population is still on 32-bit. So until they can steal my grandmother's credit card using our 64-bit mode, then that's all they'll want to port. The other thing is that this must be run on real hardware. Virtual machines, one of the ways that they intercept calls and keep themselves running is that they actually play with the TLB themselves, which is a fun bug to track down. Otherwise, and virtual machines are extremely detectable, so if you're running your code inside of a virtual machine, it's not going to really work. But the nice thing is that you can create a hardware version of a virtual machine pretty easily with minimal hardware. And again, you should probably use an isolated network. One of the other things that we noticed is that you shouldn't have a kernel debugger attached, because strange things will happen. We were pretty concerned when we got a kernel trap when we were debugging the kernel with a userland process running tlock. But you just detach it and it goes away. So today we'll be releasing the dynamic instrumentation version of Saffron, and later we'll be providing a package version of the Saffron kernel, and we'll implement a custom hardware solution and basically make it so you can do drag and drop unpacking. And then the next step after that is integrating this into Offensive Computing's database. So it's a good time for questions. I'd like to thank my advisor, Lori Liebrock, Houdini, Escape, BugCheck, Skywing, Ty Bodell, everybody on Uninformed and VAX. So if there's any questions.
We have a bit of extra time, too, and we have one other demo. Can we show that one real quick?
So just to, we'll go through each of the unpackers here.
Yeah, just to sort of show how well it does against a wrong movie player.
Looks like it's working. So what we're going to do is we're running it against ASPack, and this actually finds the original entry point here. We'll try AS Protect as well. That magical address that we showed you, again, appears correctly. FSG, again, finds that same address. The first hit, we see an execute into that page. We'll take a look at mu. Same thing, we find that execution. And each time you see one of those lines with the addresses and executions, we're creating successful dumps. And we went and validated all of those with IDA, and it worked great. P compact too, you find the same ones here.